Hello and welcome to Weapons of Math Instruction. This video is going to kick off a new playlist called Uncommon Integration Techniques. If you've taken Calculus 2, you learned a whole host of techniques of integration, such as use substitution, integration by parts, trig substitution, partial fraction decomposition, yada yada yada. In this series of videos, I'm going to present several techniques of integration that don't appear in a calculus book. This playlist will be geared towards calculus instructors and also calculus students who want to expand their integration toolbox. In this first video, I'll be talking about Laisant's theorem. So this video is divided into three segments, and in the first segment here, I'll present and prove the theorem in the title screen. So here's the theorem, and it was proved by Charles-Ange Laisant in 1905. Let f be a differentiable function with a differentiable inverse, denoted as f inverse. And let capital F be an antiderivative of little f. Then, the integral of f inverse of x dx equals x times f inverse minus capital F composed with f inverse of x plus the usual additive constant. Now notice something. On the right side here, the antiderivative of f inverse is never explicitly referred to. The only antiderivative that we see is the antiderivative of f. And this tells us something. Namely, that Laisant's theorem is useful for finding antiderivatives of inverse functions, in particular, inverses that are difficult to integrate. So the basic strategy goes like this. If you're faced with a difficult integral, so integral g of x dx, check to see if g has an inverse function. If g is invertible, then try to invert it. That is, try to find some function f of x such that g of x equals f inverse of x. And we do this in the hopes that f is easier to integrate than f inverse. And if f is easy to integrate, then apply Laisant's theorem, and you've cracked the integral of f inverse. Okay, so I'm going to clear everything but the theorem off the slide here, and we'll prove this thing. So we start by doing a change of variable. So we're going to let x equal f of w, so the new variable is w. Alright, so that means that w equals f inverse of x. If you just apply f inverse to both sides of this substitution, you get w equals f inverse of x. And dx is just the differential of f of w. So the integral of f inverse of x dx becomes the integral of w df of w. Next, we'll integrate by parts using these parts here. So u equals w, dv equals df of w, and calculating the other two parts, we get du equals dw, and v equals f of w. So here I've applied the integration by parts formula. So here's my uv, which is wf of w, and minus the integral of v du, which is the integral of f of w dw. Now, the change of variable has served its purpose, so I can go back to x now. So I'll do that here. So w is f inverse of x, and f of w is x. And this here is the antiderivative of f of w. So the antiderivative of little f is capital F, and w is f inverse of x. And here's the constant of integration. And that's it. That's the proof. When Laisant discovered this in 1905, he could not believe that it was an original result. After all, people have been doing calculus for centuries, and for this simple result to have gone undiscovered until the early 20th century seemed incredible to him. Nevertheless, Laisant was the first to find it. So as you can see, this can be taught to any calculus student who has learned integration by parts. So, if you're a calculus instructor and you find yourself a little ahead of schedule in your syllabus, consider teaching this neat result to your students. Also, consider doing me a solid and sharing a link to my video with your students. It would help me out a lot to get the views. When Laisant proved this theorem, he explicitly used the differentiability of f and f inverse as assumed here and here. But in 1994, Eric Key proved a stronger version of the theorem in which he did not make those assumptions. I'll post a link to Key's paper in the description. In the second segment of this video, I'll use Laisant's theorem to integrate the natural log of x. And this is a canonical example that every Calculus 2 student learns how to work out using integration by parts. So here at the top of the slide, I've written down Laisant's formula for reference. And let's consider the integral from the segment title, integral of natural log of x dx. So we're going to let the natural log of x be f inverse. And we know that the natural log of x is the inverse function of e to the x. And we also know that an antiderivative of e to the x is just e to the x itself. So now let's apply Laisant. So x, f inverse of x, in this case, is x natural log of x. And capital F of f inverse of x is e to the natural log of x. And we could clean this guy up just a touch. What we have here is the exponential function in base e composed with the natural logarithm. And that's just going to be x, because these two functions are inverses of each other. And aside from that one small simplification, we were essentially able to just write down the antiderivative of the natural log of x directly from Laisant's formula. In the final segment of this video, I'll use Laisant's theorem to work out this beast of an integral. Before we get started, I'll note that since square root x squared plus 1 is always greater than x, the expression inside the logarithm is positive for all x. So this integrand is defined for all x. So we'll apply the strategy that I outlined in the first segment. We'll start by asking the question, is the integrand an invertible function of x? So we'll start by taking the derivative of the integrand. So as we all know, the derivative of the natural log of some expression u is u prime over u. So up here I have u prime, and down here I have u itself. And we'll clean this up a bit. So here in the second term of the numerator, I've canceled these 2's, and I put this expression back into radical form. And the next thing I'll do is I'll clear this ugly complex fraction by multiplying the top and the bottom by the square root of x squared plus 1. So when I distribute this radical here over the two terms in the numerator, I get the square root of x squared plus 1 plus x. And when I distribute this radical here over the two terms in the denominator, I get x times the square root of x squared plus 1 plus x squared plus 1. Now I've already noted that the square root of x squared plus 1 is always greater than x, so the numerator is always positive. And it's also true that x squared plus 1 is always greater than x times the square root of x squared plus 1, and so the denominator is always positive. So the derivative of the integrand is greater than 0 for all real x. Since that's the case, the natural log of x plus the square root of x squared plus 1 is monotonically increasing on the whole real line. So this integrand is 1 to 1 and therefore invertible. So let's invert it. So let y equal the natural log of x plus the square root of x squared plus 1. And you know the drill. We start by swapping x and y. So here I've done that. Then we solve for y to find the inverse. So in this step here, I've exponentiated both sides of the equation in base e. And now I'm essentially solving a radical equation. So the way we do that is we isolate the radical and square both sides. So here I've isolated the radical by subtracting y from both sides. And here I've squared both sides. So in the next step, I'm going to FOIL out the left-hand side. So foiling this out gives me e to the 2x minus 2e to the x times y plus y squared. And squaring the radical gives me y squared plus 1. And these y squareds are going to neatly cancel out, which is fortuitous, giving me this, with a little rearrangement. 2e to the xy equals e to the 2x minus 1. And we can solve this for y by multiplying through by e to the negative x and dividing by 2 to get this. Y equals e to the x minus e to the negative x over 2. Now I want to point something out. This is the hyperbolic sine function, which means that our integrand is the inverse hyperbolic sine function. Now, it's not necessary to know anything about hyperbolic trig functions in order to do this integral. We could just work it out using these exponential functions. But I just pointed it out because I think it's kind of neat. So note something here. The integral of the hyperbolic sine function is e to the x plus e to the negative x over 2 plus c. But this guy is the hyperbolic cosine function. So this function right here is easy to integrate, which means that we can readily apply Laisant's theorem. So, pitter patter, let's get at her. At the top of the slide here, I have Laisant's formula for reference. And we're going to consider the integral from the third segment title. Integral natural log x plus square root x squared plus 1 dx. So we'll take f inverse of x in Laisant's formula to be the natural log. So that means that f of x is the hyperbolic sine function, and capital F of x is the hyperbolic cosine function. So let's chuck these into Laisant's formula. So this integral equals x f inverse of x, so this is the f inverse right here, minus capital F, which is the hyperbolic cosine, composed with f inverse, which again is the natural log, plus c. Now, the integration is now done, and we could totally stop here. But what if hyperbolic trig functions aren't a part of your syllabus? What if we had to do this whole thing in terms of exponentials? I'll revert back to exponentials and clean this up for you. So here, I've used the definition of the hyperbolic cosine to rewrite the second term on the right-hand side. And here, in this second term on the right side, I've used the fact that the natural logarithm function and the exponential function in base e are inverses of each other. Now I'm running out of room, so I'll carry this last line to the top of the next slide. There we go. And I want to focus on this ugly cuss right here. So to clear this complex fraction, I'll multiply the top and the bottom by x plus the square root of x squared plus 1. So in the numerator, if I distribute these terms over these terms, I get x plus the square root of x squared plus 1 squared plus 1. And in the denominator, I didn't bother distributing. I just put the 2 and this guy next to each other. Now in the numerator, if I FOIL this thing out and collect like terms, I get this. 2x squared plus 2x square root x squared plus 1 plus 2. All over this same thing down here. Now notice, there's a common factor of 2 in the numerator and denominator, and we can cancel those like so. And notice one more thing. I can think of this x squared plus 1 as the square root of x squared plus 1 squared, and I can factor out the square root of x squared plus 1 from each term in the numerator, like this. Now when I do that, notice there's another common factor in the top and bottom. This one. Square root x squared plus 1 plus x appears here and there, and so I can cancel those out. And this ugly looking term simplifies rather neatly to just the square root of x squared plus 1. So to wrap this up, we have that the integral of the natural log of x plus the square root of x squared plus 1 dx equals x times that same natural log plus the square root of x squared plus 1 plus c. And that's it. Thanks for tuning in to Weapons of Math Instruction. I'll be at you in a couple of days with another uncommon technique of integration. Hey everybody, if you enjoyed this video and want to see more like it, then please do follow me on my socials. You know you want to.